Welcome to Phantastic Physics. Today we're going to be talking about waves, something called constructive and destructive interference, standing waves, and something called harmonics and mode shapes. So all of these topics are going to be discussed in this demonstration. Essentially, I have a vibration generator hooked up to this string. The string is connected over here to this clamp, and it's got a certain amount of tension in it, and you can adjust the tension by moving the clamp further or just tightening the string. But before I get into today's demo, I'd like to remind everyone out there that if you enjoy the topics discussed in today's video and you want to see more, you can click the link to the Phantastic Physics store in the description below. We sell a full year high school physics curriculum, perfect for teachers, for homeschool teachers, for parents, and for students who just want to brush up on their physics. Okay, let's jump into our demonstration. So I have this machine here that lets me adjust the frequency of the string. And really what it's doing, it's adjusting the frequency generator so that it vibrates at different frequencies. And right now I have the frequency set to, let's go with 12 Hertz. And so when the frequency is at exactly 12 Hertz, what's happening here is this thing's moving up and down at 12 times per second. It's sending a wave through the string with a frequency of 12 Hertz. That wave is hitting this boundary and it's reflecting back. And those waves are continuously going in this direction and reflecting back in that direction. Well, the reason why it has this shape now, if you look at the string, it kind of looks like, students or kids playing jump rope, right? If they shake that rope up and down, you get this kind of big amplitude in the middle. And so what's happening is the wave that's being sent in this direction is actually passing the reflecting waves. So remember, they're hitting this boundary and they're bouncing back. And so as the waves moving in this direction and the waves moving in this direction meet, what happens is their amplitudes actually add together in the center. And this high point where the amplitude's really big, so if I were to draw this like this, we call that point an antinode. So an antinode is a place where the wave in this direction is interfering with the wave in that direction, and their wave amplitudes add together and you get this sort of maximum point in the wave structure. Okay, so that's called an antinode. Now, if you look at these 2 points, that's basically the boundaries over here, and those are called nodes. And a node is a place where the waves are destructively interfering, meaning that the wave moving in this direction and the wave moving in that direction, they actually cancel out at the boundaries. Okay, so we have nodes, which are places of destructive interference where the two waves cancel, and we have antinodes, which are places of constructive interference where the two waves add together. Now, what's interesting is I actually already measured the length of the string, and so the length of the string is written here. It's 0.95 meters, so it's 95 centimeters, just under a meter, about 5 centimeters less. And one more piece of information I'm going to give here is we can actually calculate the velocity of the wave moving through the string. And all we have to do is take the frequency that's being produced by this generator and multiply by the wavelength. And so first we have to figure out, what is the wavelength of this wave? And so if you look at the characteristics of any full wave, a wave can be modeled with, basically it starts with a node, goes up to what's called the crest or the highest point, and then it drops through another node, it hits what's called the trough or the lowest point, and then returns back to a node again. So this full up and down shape is what we define as one wavelength. And so my question to you out there, audience, is how many wavelengths do you see in this shape here? And so if you think about it, we have a node here, it hits a maximum point and then comes back to a node. That's actually just 1/2 of a wavelength. So this shape that I've produced here is producing exactly 1/2 of a wavelength. So if I wanted to calculate the velocity or how fast this wave is traveling through the string, I would take the frequency, which my machine actually tells me is 12 Hertz. So I'm going to type in or write 12 Hertz. And I'm going to multiply by the wavelength. And remember, this is half of a wavelength. So you can imagine that if I had 2 of these, I would have a full wavelength. So I need twice the length of the string, which means 2 times this value. So I'm going to do 2 times 0.95 meters. And so now I can calculate the velocity of this wave as it travels through the string. So we have 12 times 2 times 0.95, and I get 22.8. And this comes out in units of meters per second. So that means that this wave is traveling really fast. It's actually going 22.8 meters per second. So in 1 second, it would travel 22.8 meters. So for example, if this string, instead of being 0.95 meters long, it was actually 22.8 meters long, well, that means this wave would actually get to the other side of the string in a single second. So this is the velocity that the wave is moving in that direction and then back in this direction again. And so what we have here, if you look at the shape again, where we have two nodes on the sides and an antinode in the middle, something like this, that's called a mode shape, and it's also known as a harmonic. And so this one in particular is known as the first harmonic, or the first mode shape. And now what's interesting is I can actually increase the frequency on my generator. So I'm going to go up, higher and higher frequency. And so now my generator is moving up and down faster, and it's actually at 24 hertz now. So I've doubled the frequency. And what did you notice? Well, the mode shape has changed, right? So it's kind of this like S pattern now, where you have two nodes on the side, but we have a new node in the middle, right? And so if I were to draw this, the shape actually looks like this now. We have a node, then it goes up, down, up again, and it's kind of doing this. And so this is a node, that's another node, that's another node. So the nodes are the places where the two waves are canceling out. And remember, it's a wave moving in this direction, hitting the boundary and bouncing back. And so those incoming and outgoing waves are meeting, and they're fully canceling out here in the center and on the sides. But we also have antinodes here and here. So there's two places where when the waves meet, they actually add their amplitudes together and you get these two local maxima, okay? So this is called the second mode shape, or the second harmonic. And so now what's really interesting is I can run my velocity equation again and see if I get 22.8 meters per second this time. And the reason I'm expecting the velocity to be the same, let me write this on the side so I don't forget, is that the velocity of any wave moving through some medium has to be constant. So for example, a sound wave, like the waves I'm producing by talking, sound travels at 340 meters per second, give or take, at sea level. So when the air is at that particular density at sea level, we expect sound waves to always travel at about 340 meters per second, and that is a constant speed. The only way to change the speed of any wave through a medium is to change the medium, which means if you're an aircraft, you would have to go to a higher altitude where the air is less dense, and then sound would travel at a different speed. But again, bringing it back to the string, because this string hasn't changed at all, it's the same medium, I expect the velocity of this wave through this string to be constant. So then if the velocity doesn't change of a wave through a particular medium, that means only the frequency and the wavelength can change, right? So if I increase the frequency, the wavelength would have to drop so that this stays constant. Or if I were to decrease the frequency of this machine, the wavelength would have to increase so that this velocity stays the same. So now looking at this second mode shape, or the second harmonic that we have produced here, how many full wavelengths do you see here? Well, there's actually one, right? Remember we said a wavelength will look like this. And so you would have here, it passes up through the crest, goes back to a node, to a trough, back to the crest again, or sorry, back to a node again. You're getting one full wavelength in this mode shape. So that means when we do the frequency times the wavelength, I can use just the full length of the string for my wavelength. So the frequency here says 24 hertz. So I'll plug that in. Remember, that's the number of times per second that this machine is moving up and down. The wavelength of this wave is one full string length, which is 0.95 meters. And so if I multiply 24 times 0.95, I get exactly 22.8 meters per second, which is really phenomenal because I've proven that the velocity, the speed of this wave traveling through the string and bouncing back again, has not changed when I increased this frequency and got a totally different mode shape. The wave is still traveling at the same velocity. So now I can increase this frequency even further, and you'll see another interesting thing happen right here. And so now this machine is moving 37 times per second. It has a frequency of 37 hertz. And how many waves, or full wavelengths do you see in this particular mode shape here? This is called the third mode shape, or the third harmonic. Well, I'm looking and I see it starts at a node, it goes up, passes a node again, and back to a node. So right here, is a full wavelength. And so I have one wavelength plus an extra half of a wavelength. So how long is my wavelength then? Well, it's 2/3 of the length of the string. So again, I can calculate the velocity in this string by taking the frequency, which says 37 hertz on my machine. And remember that one full wavelength here is 2/3 of the overall string length. So I'm going to do 2/3 times 0.95. And so if I type that in my calculator, I actually get 23.43 meters per second. And so you might be wondering, why is this a little bit off of this? Well, it's because my machine doesn't read out like partial frequencies. It says 37 hertz, but I have a feeling it's something closer to 37.5 hertz. So because the degree of accuracy isn't very precise on this readout here, I'm getting a number that looks a little bit off. But accounting for that error, it's actually the same value. It's really, really close, actually. So again, this is called the third harmonic or the third mode shape. And so if you count how many nodes do you see? I see 1, 2, 3, 4 nodes. And then how many antinodes? Well, that's how many local maximums you see. I see 1, 2, 3 antinodes, okay? So now let's move the frequency up even further. And wow, look at this shape here. So you can see now this is the fourth mode shape or the fourth harmonic. And if we were to count the nodes, I see 1, 2, 3, 4, and 5. Remember, nodes are places where the wave in this direction and the bouncing back wave, when they meet, they fully cancel out in these positions and at the edges, okay? How many antinodes do you see? Well, how many places do you see the waves combining amplitudes and becoming a large amplitude wave? I see 1, 2, 3, 4 antinodes. Okay, so the fourth mode shape or the fourth harmonic has 4 antinodes and 5 nodes. Okay, so I can run the velocity calculation for this mode shape too. So I have 49 hertz is my frequency. And so how many wavelengths do you see in this string here? Well, if I start here and look, there's one full wavelength right there, and then there's another full wavelength. So I actually have 2 full wavelengths in this shape here. And so that means if I look at how long is one wavelength, it's exactly half of the overall string. So for my wavelength, I'm going to plug in half of the string's length. So we have 0.5 times the length of the string, which is 0.95 meters. And so if I run this calculation, 49 times half of the string length, I end up with 23.28 meters per second. And again, it's a little bit off, but that's again mainly because my frequency generator screen is not showing me partial frequencies. So I have a feeling it's not exactly 49 hertz. It may be something like 50 hertz. But yeah, so this is the fourth mode shape, the fourth harmonic. And now let's turn it up even further. And as I increase that frequency, you may be able to see, it's harder to see them at the higher mode shapes because the amplitudes start to get even smaller. But if you look closely, there's a node here, 1, 2, 3, 4, 5, and 6. See if I can adjust this a little bit. There we go. And then there's an antinode, 1, 2, 3, 4, and 5. And so this is the fifth harmonic, or the fifth mode shape. And I could continue on and on and on, right? So what have we learned today? Well, we've learned that if you send a wave through a string and hit a hard surface and bounce back, the waves in this direction will interfere with the waves that are returning, and sometimes their amplitudes will add together and you'll get something like this, and then sometimes they'll cancel out and you'll get a node there. And by the way, I don't think I used this term today. This is what we call a standing wave. It's that phenomenon of producing a wave that travels in one direction, reflects, and interferes with itself. So that's a standing wave. And we also learned the different mode shapes and the different harmonics can be created by just adjusting this frequency, which causes your wavelength to also adjust as well. But we also saw that the velocity velocity of the wave, no matter how high the frequency gets or how small the wavelength gets, will always be essentially constant, because the velocity of a wave cannot change unless you change the medium through which it travels. So for example, a wave traveling through the air is going to have a different velocity than the same wave traveling underwater, right? And actually the speed of sound in the ocean or underwater is significantly faster than the speed of sound through the air. Thank you for watching Phantastic Physics. Please like this video and subscribe to our channel if you want to see more interesting physics content. Goodbye for now, and remember, it's a fantastic universe out there, so stay curious.